We physicists have stood firm for 100 years, beginning in about 1916. This picture presents a local dark entrance that could very well be among the most enticing peculiarities of the universe that baffle us. They are enormous monsters in terms of drive, but simultaneously, for all intents and purposes, unseen by us. A dark opening possibly weighing 2 to 4 million times the mass of the Sun. However, considering the investigation that was put into them over the last 2 or 3 decades, we have gone from knowing literally nothing about them to learning more up close and personal. Things have recently become even more insane. Michio Kaku reported that we have finally looked at what lies within a gloomy opening, and this new data sheds light on nuances the scientific universe might have missed right from the beginning. Join us as we dig deeper into the shadowy passageways and uncover space's immense and terrifying contents. Before we enter the subtleties of what Michio Kaku found, we must discuss the fundamentals. While the majority of us have a rough idea of what dim openings are, there are still a few gaps in our knowledge. In 1916, Albert Einstein published his theory of general relativity, which predicted the presence of dark passageways. At the time, the idea of dark openings was purely theoretical, requiring an additional 50 years for the scientific community to locate evidence that they actually exist. This occurred in the 1960s when scientists were studying the Cygnus X1 heavenly body and observed an odd, radiant blue star producing X-rays. It was clear that this star was not a stable object but was instead orbiting a gigantic, dark mass. Further examination revealed that the X-rays weren't just moving randomly, they were being sucked into the dark object they circled. Hence, the name dark opening, or black hole. This discovery was huge because it demonstrated that black holes do exist. They were not merely a creation of Albert Einstein's wild imagination. This also meant that there was a stunning space-based phenomenon that we urgently needed to understand. Scientists from around the world went to work. The dark opening in question, known as Cygnus X1, is located in the Cygnus constellation, approximately 6,000 light-years from Earth. It was a multiple discovery, not just one, being many times brighter than the Sun and incredibly dense, giving it a strong gravitational pull. The gravitational pull of a black hole is so strong that not even light can escape it, which is why it is called a dark opening. The concept of a black hole is both intriguing and terrifying, a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close is sucked in and lost forever. But that element of danger makes it even more crucial to understand everything about them. Was this the end of our discoveries, or were we just beginning? The answer turned out to be the latter. Following the discovery of Cygnus X1, researchers began searching for other black holes. They found that there might be nearly 100 million black holes in the Milky Way alone. However, because they are extremely difficult to detect, we still don't have an exact count. By all accounts, several million black holes exist in the Milky Way, our own galactic backyard, making their study even more important. The main issue with black holes will always be gravity. Their gravitational pull is so intense that anything entering is cosmically compressed until it becomes a singularity. In simpler terms, black holes act like massive vacuum cleaners, pulling everything in. One of the most shocking aspects of black hole research is the fact that if someone were to fall into one, they would reach a stage where they become a single line, a process that would occur slowly, causing death long before the full force of reality sets in. So, let's just say that nobody should ever step into one. But since they are everywhere, could we be in danger? The closest black hole to Earth is around 500 light-years away, still close enough to raise multiple concerns. In 2021, researchers managed to capture the first clear image of a black hole, the M87 black hole. This image was taken over multiple nights, and scientists compiled the data from each image, aligning individual photos to fill in the gaps. Through this process, they determined that black holes consist of 3 layers, rather than just being a single void of nothingness as many people believe. To reach the nothingness of a black hole, you must first pass through 2 layers. The first is the event horizon, the point of no return. Once you cross this boundary, the only possible path is forward, into the black hole. From there, things get worse. The second layer is the photon sphere, where light gets trapped by the black hole's gravitational force and cannot escape. Finally, the third layer is the singularity, the point in spacetime where all matter is compressed infinitely, and the known physical laws break down. At this point, we have no way of predicting what happens next. To make things even more complicated, each black hole is different. While they all follow the same 3-layer structure, their behavior can vary drastically. If we want to understand them better, we need to return to our telescopes and study the basics in depth. But this is no simple task. Since black holes do not emit light, researchers must investigate them indirectly by studying their emission of radiation and the gas and dust surrounding them. Sending a probe into a black hole is impossible. Once it crosses the event horizon, it is drawn toward the singularity, where it is compacted into an infinitely small point. Because of this fundamental challenge, researchers must study black holes in a two-dimensional way, despite their three-dimensional nature. To make matters worse, each black hole is unique, and the physical laws we rely on break down inside them. This means traditional scientific methods often don't apply. That doesn't mean researchers aren't trying. There are numerous theories and explanations for black holes, each adding new layers of complexity. One of the most captivating theories involves how black holes form. They originate when a massive star collapses. When a star exhausts its fuel, it can no longer generate enough energy to counteract gravity's inward pull. As a result, the star begins to implode, shrinking and becoming denser. If the star is massive enough, this process can lead to the formation of a black hole. If the collapsing star is large enough, its core contracts under its own gravity, reaching an incredibly dense state. At this point, the escape velocity, the speed required to break free from its gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, not even photons can escape, resulting in a black hole. This process leaves behind what is known as the event horizon, the boundary beyond which nothing can return. The star's core continues to collapse until it forms a singularity, a point of infinite density where space and time cease to function as we understand them. The mystery of black hole growth. While some black holes form from collapsing stars, others grow to be supermassive, containing millions to billions of times the mass of our Sun. Scientists are still trying to determine how these enormous cosmic giants form. Some theories suggest that they start small and grow by consuming surrounding gas, dust, stars, and even merging with other black holes. These supermassive black holes are often found at the centers of galaxies, including our own Milky Way, which harbors Sagittarius A*, a black hole approximately 4 million times the mass of the Sun. Observations suggest that these massive objects play a crucial role in shaping galaxies, influencing the motion of stars and even regulating star formation. The role of black holes in the universe. Despite their destructive reputation, black holes may actually be essential for the universe's structure. As they consume surrounding material, they release immense amounts of energy, generating powerful jets of radiation that can affect the formation of stars and planets. Some scientists theorize that without black holes, galaxies as we know them might not have formed in the same way. Additionally, black holes are at the center of some of the most exciting modern physics research. They challenge our understanding of gravity, quantum mechanics, and even time itself. Scientists hope that studying them will help bridge the gap between Einstein's theory of general relativity and quantum physics, leading to new discoveries about the nature of reality. What lies beyond the event horizon? One of the biggest mysteries surrounding black holes is what happens beyond the event horizon. Since nothing can escape, we have no direct way of observing their interiors. Some theories suggest that matter falling into a black hole is destroyed at the singularity, while others propose that it could be transported elsewhere, perhaps into another universe. This idea is related to wormhole theories, which suggest that black holes could serve as portals to other parts of the cosmos or even different dimensions. However, there is no observational evidence for this, and the extreme conditions inside black holes make it nearly impossible to test these theories. The future of black hole research. With advancements in technology, we are entering a new era of black hole exploration. The Event Horizon Telescope, EHT, which captured the first-ever image of a black hole in 2019, continues to provide groundbreaking data. Future telescopes and space missions may allow us to study black holes with even greater precision, offering new insights into their behavior and their role in the universe. One exciting possibility is the detection of Hawking radiation, a theoretical form of radiation predicted by physicist Stephen Hawking. If confirmed, this would revolutionize our understanding of black holes and could even suggest that they slowly evaporate over time. Conclusion. Black holes are among the most mysterious and fascinating objects in the universe. From their formation through stellar collapse to their potential role in shaping galaxies, they continue to challenge and expand our understanding of physics. As scientists push the boundaries of observation and theory, we may one day unlock the deepest secrets of these cosmic enigmas. Until then, black holes remain both a source of wonder and a reminder of how much we still have to learn about the universe. It becomes a singularity to comprehend the idea of dark openings. NASA researchers delved deeply into their study, focusing on the center of the universe. In M87, astronomers discovered a truly powerful, extremely hot whirlpool of hydrogen gas rotating at an alarming rate, 1.2 million meters per hour. The sheer force of the gas disk's rotation should have caused it to splinter violently in all directions. However, it didn't. The researchers concluded that an immense mass at the galaxy's center was preventing this from occurring. This enormous object weighed between 2 and 3 billion suns, and the opening had to be dark. But that isn't the only theory about dark spaces. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's gravity equations to provide the best description of a rotating dark opening. He demonstrated that the dark opening would not collapse into a single point, as previously thought. Instead, it would form a fireball or a thin disk. The disk would rotate so quickly that outward forces would prevent it from collapsing. This disk of matter is called the ergosphere, a region surrounding the mysterious opening where the laws of physics begin to break down. However, the most fascinating aspect of Kerr's solution was that it foresaw the existence of the Einstein-Rosen bridge. This is a wormhole, a theoretical passageway through space and time that connects two distinct regions of the universe, or even two parallel universes. The idea suggests that instead of being crushed into oblivion upon entering a dark opening, one could be sucked through a ring-like structure of fire and ejected through a white hole into a parallel universe. To understand how this works, we must examine Einstein's concept of spacetime. The reality we experience does not consist of independent entities but is interconnected, forming a four-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating a gravitational field that influences the movement of other objects. Now, picture a piece of paper representing spacetime. If you place 2 points on it and draw a line between them, this represents the conventional way things move through time and space. But imagine folding the paper so that the 2 points touch. This is the basic idea behind a wormhole. It is a shortcut through spacetime, connecting two distant points instantaneously. Wormholes aren't merely a concept from science fiction, they are actually a prediction of general relativity. However, no one has observed one directly, likely because wormholes are inherently unstable and would collapse very quickly. The presence of an Einstein-Rosen bridge suggests that dark openings are not just vast vacuum cleaners but could also be portals to other regions of spacetime. Could we travel through a wormhole? Sadly, the answer is probably no, not yet. Even if we could stabilize a wormhole, using it to travel faster than light would contradict Einstein's theory of relativity, which states that the speed of light is the ultimate speed limit. However, the idea that wormholes and dark openings could be pathways to other parts of the universe, or even other timelines, is a topic of ongoing speculation among physicists. The possibility that spacetime could permit shortcuts across vast distances, or even allow for time travel, is revolutionary, if it could ever be achieved. One of the most captivating concepts in this field is the CR wormhole, named after mathematician Roy Kerr, who first described it using Einstein's gravity equations. This type of wormhole is essentially a conceivable tunnel in spacetime that could link two distant locations, perhaps even two separate universes or different times within the same universe. A wormhole, in a sense, is like a ring-shaped portal, similar to the mirror in Alice in Wonderland, capable of transporting a traveler to a different universe or time period, where the laws of physics might differ from what we know. While the possibility of using wormholes for interstellar or time travel is exciting, it remains a topic of debate among physicists. Some argue that wormholes, especially traversable ones, may be too unstable due to the extreme radiation and subatomic forces surrounding their entrances. Critics also point out that Einstein's equations, which describe wormholes and dark openings, only apply to gravity, not to the quantum forces that govern radiation and subatomic particles. To truly understand these phenomena, scientists believe we need a theory that unites quantum mechanics with gravity, a theory of everything. This hypothetical framework would combine Einstein's theory of gravity with quantum mechanics. One of the most promising approaches to this is superstring theory. This theory suggests that subatomic particles are not point-like but are instead tiny, vibrating strings. These strings, much like musical notes on a violin, correspond to different fundamental particles based on their vibrations. One of the fascinating aspects of superstring theory is its implication that as strings move through time, they alter the fabric of space itself. This could create wormholes and dark openings, offering strange but possible solutions to Einstein's equations. In this sense, superstring theory is more than just a quantum theory of gravity, it also helps explain many mysterious phenomena in the universe. However, there's a catch. Superstring theory requires additional dimensions of spacetime, so small that we can't directly observe them.